Assalamualaikum warahmatullahi wabarakatuh. My name is Ifa Auni binti Zakaria.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Afika binti Syahrum.
Assalamualaikum warahmatullahi wabarakatuh. My name is Mariam Jamila binti Muhammad Saifuddin.
This is some of our data, years of experience, VL Selling. To begin, our dataset consists of 30 data points that demonstrate the relationship between years of experience and salary. Here, the independent variable is the years of experience, which influences the dependent variable's salary. Our primary goal is to analyze this relationship to understanding whether having more experience significantly impact on an individual salary. We also want to see if the salary increase proportionally with experience or if other pattern emerge. This data set was obtained from Kaggle, a platform known for providing high quality for data analysis. The primary objective of our project are as follows. First, we aim to identify the mathematical function that best fit the dataset. To achieve this, we evaluate and compare the sum of square errors or SSE values for each function. A lower SSE value means the function better represents the relationship between years of experience and salary. Second, we aim to use the best fitting function to predict future trends in the dataset. By applying the most accurate model, we can forecast potential outcomes and gain insight into how salary may evolve as years of experience increases. Together, this objective enables us to analyze the dataset comprehensively, ensuring that our conclusions are both accurate and practical. To analyze the dataset, we use the least square method, a mathematical approach that minimizes the differences between the observed and predicted values. We apply three techniques: a linear model to fit a straight line trend, a polynomial model for more complex relationship, and transcendental models such as exponential or power law function to account for nonlinear pattern.
The least square linear function is a mathematical approach used to determine the best fit line that models the relationship between two variables in a dataset. The least square linear function is a method used in statistics and mathematics to find the best fit line through a set of data points. This method can minimize the sum of square of the vertical differences, which is residuals between the observed values and the values predicted by the line. By optimizing the slope and the intercept of the line, this method ensures the overall error is as small as possible. Thus, it does make the least square function a method that widely used in the regression analysis. For step number 1, we need to form a matrix function. Okay, why do we need to use matrices? We use matrix when determining the least square because it allows us to organize the problems efficiently and can handle multiple equations systematically. So, as you can see in the second step, we had entered the value of the dataset into the calculator and had gained the values according to the step 1. So next is, we can also gain the value of A0 and A1 by using the regression mode in the calculator. So last but not least, we entered the value of A0 and A1 into the formula and we had obtained the new derived function, which is yx equal to A0 plus A1x. The first picture represents our data, which is X is years of experience and Y is the salary. So the last column is the approximation of Y. We had obtained these values by entering it into the formula that we had gained before, which is Yx equal to A1 plus A1x plus A0. And the second picture is the scatter plot of the least square function. Next is fitting a least square polynomial function. Approximate a set of data points by finding a polynomial of a specific degree. So, the coefficients are determined by solving a system of linear equations derived from minimizing the sum of square error, which is SSE. This method is widely used in data fitting, regression analysis, and signal processing, as it provides a smooth approximation to noisy data. However, it can lead to overfitting if the polynomial degree is too high and may perform poorly when extrapolating outside the data range. So as usual, we use matrices form to represent the function. We enter the value into the calculator and gain its values, then rewrite it into the matrices form. After a long journey of calculating, we had obtained the values of A0, A1, A2, A3, A4, A5, and also A6. Then lastly, we enter all the values into the formula in the step 4. The first picture is the dataset of the year's experience and salary, and also the last column is the Y approximation, and we had gained the Y approximation by using the formula that we had gained before. And the second picture is the scatter plots of the least square polynomial function.
So for our last method, using fitting transcendental function, for this method, our group choose the rational function y equal to ax over b plus x. So to linearize the rational function, we apply a transformation by taking the reciprocal of both sides. This gives us 1 over y equal to b over a multiplied of 1 over x minus 1 over a. By introduction, the substitution, v equal to y equal to y per y and x equal to y per x. So the equation takes a linear form, y equal to a1x plus a naught, where a naught equal to 1 per a and a1 equal to b per a. This transformation allows us to convert the nonlinear relationship into a linear model, making it easier to estimate the parameter using standard regression technique. Once an a0 and a1 are determined, we can recover the original parameter as follows: a equal to 1 over a0 and b equal to a1 multiplied of a. So why we choose this function? The function is simple and easy to use. It gives a smooth curve that looks realistic and avoid the problem of using more complicated models like a higher order polynomial. That's why we choose the function as the best one of our analysis. This function is good because it matches how salaries grow in a real life. At the start of career, salaries grow quickly, but after some time, they stop growing as fast and become stable. This is called a plateau, and it happens because of things like company budgets, limits on promotion, and salary caps in industry. This approach works well because it combines realism and mathematical simplicity. The rational function reflects real-world trends of rapid salary growth early in a career and stabilization over time. It avoids the pitfalls of overfitting and unnecessary complexity seen in higher order polynomials. Additionally, the linearization process makes parameter estimation straightforward and ensures the function remains easy to interpret. This advantage makes it the best choice for our analysis. Next, as shown on this slide, there is sum of the table of a new y and new x and also the approximates of y, and also the graph for this equation. Our new s is 1 over x, and new y is 1 over y. So now I will show how to get the equation from this method. First, we obtain the value of n, the number of the data, and sum of x, sum of y, sum of x power of 2, and sum of xy. After we get the value, we write the normal equation in metric form of 2 by 2. And with using equation mode in calculator, we got the value of A0 and A1. Next, we know that A0 equal to 1 over A. Using this linear, we find the value of A. And same with A1, we know that A1 equal to B over A. And after we got a value of A, we just substitute A in B over A, and we got the value of B. And lastly, the final step, after we got the value of A and B, we substitute in our function, and we got the final equation for this method.
Okay, so I will be presenting our analysis of salary prediction models based on years of experience. We evaluated 3 different mathematical models to determine which one best fits the data. So, to begin, our dataset includes salary figures corresponding to different years of experience. The goal was to find a model that best predicts salaries based on experience. We test 3 different models. First, fitting transcendental function. Second, least square linear function. And last, least square polynomial function. By comparing these models, we can determine which provides the most accurate salary prediction.
So next, we evaluate how well each model fits the data using the sum of squared error, or we can call SSE. As shown in the table of SSE, it shows that the last model, which is least square polynomial function, which I already highlight as a best fit models, which has this lowest value. As we can see, the polynomial function has the lowest SSE, meaning it is the best fitting model for this data. Based on the SSE values, the least square polynomial function provides the best fit for salary prediction. Since it has the lowest SSE, it most accurately represents the relationship between years of experience and salary. This means it can be used to make more reliable salary prediction. So, what does the interpretation of SSE means? The lowest SSE indicates a better fitting model. It is also means that the model closely approximates the actual salary data. The smaller SSE value means a model is more accurate as its predictions are closer to actual salary values. So, to conclude our presentation, in this study, we analyzed that 30 data points representing the relationship between salary and years of experience. Our goal was to determine the best fitting model among 3 methods, which are fitting transcendental function, least squares linear function, and least squares polynomial function. After evaluating the results, we found that the least squares polynomial model had the lowest sum of squared errors, making it the most accurate fit for our data. However, while high-degree polynomials are powerful in capturing complex relationships, they come with challenges such as overfitting. So, to improve model reliability, techniques like simplification, regularization, and cross-validation should be applied. Additionally, incorporating domain knowledge helps in selecting the most appropriate model. Looking ahead, future work could explore alternative approaches such as piecewise regression or machine learning models to further enhance predictive accuracy while maintaining interpretability.